Welcome. We're going to work on some anti-differentiation. The method of anti-differentiation is called u-substitution. But for some review and to make some connections, we're going to start by recalling how to differentiate, the forward process using the chain rule. We used the chain rule when we had a composition function like capital F of x here. It's not just x cubed, it's this quadratic cubed. And so to take the derivative f prime, we bring down the exponent 3 as a coefficient, multiply by the original base, subtract 1 from that exponent, but then we have to remember to multiply by the derivative of the base. So we started out with the quadratic cubed, and the derivative is 3 times the quadratic squared times the derivative of the quadratic, which was linear. Let's look at another example where we have the square root of this difference. To remind ourselves of the power rule for differentiation, we might write the square root as a fractional power. So we have the quadratic to the 1/2 power. And then to find f prime, we bring down the exponent 1/2 as a coefficient. We leave the base alone, but we subtract 1 from 1/2. Then we go back and take the derivative of the base. So this quadratic to the 1/2 has a derivative of 1/2 times the quadratic to the negative 1/2 times 2x using the chain rule. A couple more chain rule examples. Now f of x is 1 over the cortex squared. And we can use negative powers to rewrite the reciprocal of the cortex squared. So we have the cortex to the negative 2. And then when we take the derivative, we bring down the negative 2, leave the base, which is cortex, which means power 4. Subtract 1 from that old exponent. Negative 2 minus 1 is negative 3. But we don't forget, we have to take the derivative of this function that was on the inside. And the derivative of a cortex is going to be cubic. And do you see where we got that negative from in that for the chain rule? Okay, and that can be cleaned up and maybe rewrite that as positive 8x cubed out front, but we'll move on. How about something transcendental? If the original function is now sine of 5x squared, we know its derivative is going to be in terms of cosine of 5x squared. And then we take the derivative of the angle, which would be 10x. And we recall why we need the chain rule. It's not just sine of x, it's sine of the quadratic. So the derivative is cosine times the quadratic, cosine applied to the quadratic times the derivative of the quadratic. And then we might rewrite that and bring the 10x and multiply it out front. But it's still just a big product, 10 times x times cosine of 5x squared. Okay, to continue a little more quickly, still in the forwards direction, if we have this composition function e to the x squared, the derivative is almost just e to the x squared, but we have to multiply by the derivative of the exponent. So we get this factor of 2 times x. And many times you'll see the 2 times x written out front and multiplying the exponential. What if the original function is sine squared of x, which means we have sine of x times itself? Then we use the power rule first, bring down the 2, multiply times sine, drop the exponent to 1, but we still have to multiply by the derivative of the base. If you think about it, the base was sine, so its derivative is cosine. If the original function were log of this sum, then the derivative would be the reciprocal of that sum times the derivative of that sum, which is just 6x. And then many textbook publishers would take 6 times x and put that in the numerator. If the original function is arctan of 4x, we know what the derivative should look like. It's 1 over the sum, 1 plus the quantity 4x squared. But we needed another factor of 4. Why? Because the chain rule. So in summary, the forwards direction, we've had these original functions that were composition functions. And if we called the inside function u of x, then the derivative of the composition would be f prime of u of x times u prime of x. And if that's written in Leibniz notation, we see this product. And just in kind of the general rule is the derivative of a composition function is a product. So now going in the backwards direction, what if our integrand is a product? And we know already that there's not a product rule for integration, so to speak. But we can hope that this integrand is the result of differentiation using the chain rule. And if we look for a composition, and maybe in this instance we look at this difference, 4x squared minus x, and we introduce this dummy variable u. And I'm going to record that up here in the right hand corner. If u is the quadratic, and we take the derivative of u, then we get this relationship between a new differential du and the old differential dx. Now look back at our integrand. If u is 4x squared minus x, we were really fortunate to have the derivative of u as a factor over here in the integrand. So yes, since we have u times u prime, a function of u, namely 3u squared times u prime, then we can change our variable of integration to u, and we're going to be able to wrap up this little product here, 8x minus 1 times dx is du. And the technique then is to use this dummy variable in place of the quadratic. So 3 times the quadratic squared becomes 3u squared. And we have this product wrapped up in the differential du. Now we know how to do the reverse power rule. We're going to go up to a cubic. Well, excuse me, let me stop a moment. I'm just showing the reader how the coefficient of 3 was a scalar. We just brought that down. And we had this power because u was the base. And then we can go up to u cubed and divide by 3, and the resulting antiderivative would be u cubed plus c. The last step in this process is to go back, replace u with how we defined it. In this case it was the quadratic. So our answer, final answer, is the quadratic cube plus c. Second example. If we have a product in the integrand, we're hoping the product is some composite function times the derivative of the innermost function. And here, simply, we have this linear function. We can call that u. The derivative of u would be 5, and the way we're going to write that is in terms of differentials. If we get du, then we're going to take the derivative with respect to x on the right hand side, and we get this little factor of dx. For some of us, we just look, and in our mind we're going to label the sum as u, the derivative of the sum, u prime, is 5, and then 5 dx becomes du. And then we can simply rewrite the integral, the original integral, as the integral of u du. We go up to a quadratic. Our antiderivative is 1/2 u squared plus c. And then wherever there is a u, we go back and plug in 1 plus 5x. And so I'll just show you a few more examples. We're basically training our eyeballs to find a composition. And then we're hoping that the derivative of the innermost function is somewhere else in the integrand as a factor. Okay, in this case, u is x squared minus 1. And the derivative of x squared minus 1 is there in the integrand, so we call that u prime. But then this product 2x dx gets wrapped up into the new differential. So substituting u, we're going to have the integral of u to 1/2 du. And we just have to be careful. Go up to a power of 3/2. And when we take this answer in u, we have to substitute back what u had been defined. Okay, and we're going to see this in a couple more forms. What if we have a quotient? Okay, there is no quotient rule for integration. So we have to rewrite things in terms of u-substitution. And it looks like the composition is here in the denominator. We've got this quartic. We're fortunate to have a cubic up top. So if we take the difference, 3 minus x to the 4th, up here, and substitute u for that quartic, then the differential du will be the derivative of the right-hand side times dx. And look at here. We've got u of x in the bottom, u prime up top, and then this product, negative 4x cubed dx, gets wrapped up into du. And then our quotient simply becomes 1 over u cubed du. And I suppose I forgot to, in the PowerPoint, find the antiderivative. But we would rewrite this as u to the negative 3 and could use the reverse power rule. Okay, and this is going to be my last example. It'll probably kind of cut short. But check it out. U is 5x squared minus 9. The derivative of u would be 10x. I'm showing that here with Leibniz notation. To get du by itself, we can pretend that we're multiplying both sides by dx. But look, back at the original, we don't have a factor of 10. What do we do? Okay, so we rearrange our differentials and get x dx by itself. I multiply both sides by dx, divide by 10, and I get this relationship. The old, on the right-hand side, x dx, that differential expression gets simplified to du over 10. And I'm showing you that here. We can make our substitution. The quadratic to the 4th becomes u to the 4th. The old differential expression gets wrapped up into du over 10. And we can factor out the scalar, 1/10, and just treat this integral as the simple one we know. And I don't think I have that answer here for us. But thank you.